let's again examine triple integrals. And recall that sort of key thing we saw last time was that the volume if you look at delta v, that this was delta x times delta y times delta z. This is going to convert to the volume differential. So dv is dx times dy dz. But the order can be swapped around, so this could be dx dz dy. This could be dy dx dz. This could be dy dz dx. And the list goes on. There's two more. Okay, so when looking at the triple integral over a region called E of the function f of x comma y comma z dv, to write this as an iterated integral, to really write out the pieces, you're going to have maybe you have here a dx dy dz integral. So this outer integral will be z value. So like the lower z value, I'll write z min, z max. Then you have a y min and a y max. And the innermost integral, an x min and an x max of the function f of x comma y comma z. And the key comments to say here is that the x min and max, so these can just be constants, of course, that's possible, right? So these can, however, depend on y and z, or just be numbers, or just constants. That's fine. So they don't have to mention y and z, but they may. Then this next level, right, so the y min and max, these can depend on a future variable that you're going to integrate with respect to z, but not on x. They cannot depend on x. And then the outer one, z, will be the final integration that you do. So with respect to z, these must be numbers. Okay, the outermost integral always have to have numbers. So similarly, just to try to illustrate the same point again, let's say you have integral from something to something, integral something to something, integral from something to something of f of x comma y comma z. Let's say the order is now switched to be dz dx dy. So the innermost integral is the z integral. Then your z min and max, these can use or can mention x and y if you want. Okay. Then at this point, when we're on to the x integral, so this can use, we've now integrated with respect to z. So this can use y because we haven't integrated with respect to y yet, but not z anymore. And then finally, the outermost integral, this can be numbers only, or must be numbers only. Let's just say must be numbers. Cannot mention any variables there. Let's also recall a couple other things, that the area of a region D can be computed as the double integral over that region of the function 1 dA. And so similarly, the volume of a three-dimensional region E can be computed as the triple integral over that region of the function 1, the constant function 1 dV. Now, the thing that tends to be visually challenging, right? The visual challenge, this takes a little getting used to. I mean, conceptually, like what needs to happen is like, okay, sure, but really the challenging thing, I think, is given a three-dimensional region, let's say it's called E, then you have to decide on a reasonable order of integration. And you have to determine endpoints of integration. I think this is the most challenging thing. about this. It's conceptually like, oh yeah, okay, what's going on isn't so bad, but it's you've got this shape, you've got this three-dimensional thing, and you've got to think about how to describe it, and it has to do this, cascading of things of what can depend on what, and an order has to be selected, and how do you do all this stuff? This challenge is simplified a little bit. Not saying that this solves all your problems right away, but use projections. Okay, so what you do is after finding the appropriate bounds, the correct, of course, the bounds, the correct bounds for the inner integral, then project the coordinate away. So what do we mean by project? So let's clarify, because this word just sounds fancy, I think. Project. And let's just clarify what this is really just trying to get at. Much fancier word than I think is perhaps needed, but it's the kind of usual language that gets used for this. So you're trying to set up some integral here. Integral something to something, next integral something to something, integral something to something of your function. And let's just say you have, I don't know, just say the order for now, dz, dx, dy. Let's say you decided that was the right order. Okay. So once you get these, the bounds for z, then what you're going to do is project in the z direction, and what that means is then in xy there's going to be a shadow, let's say, of this shape E, up here, on the xy plane. So then here's the thing. What we mean by this projection is it's just really a smooshing. It's just take the object you have and just let all of the points of the object just live in the xy plane. So what really happens is that the points that are above the xy plane move down. That's what the projection does. It moves them down into the xy plane. Similarly, points that were below the xy plane move up into the xy plane. Okay, so the basic idea behind this is to imagine losing depth perception. So we will look at some examples in a moment, but just to try to make sense of this, let's take a look at a second example here. So second example, this is a little abstract still as written, but let's just say you had an integral from something to something. We're trying to figure out what these somethings are. Integral something to something, and integral something to something of your function f of x comma y comma z. And let's say now the order is dy, dx, dz. Then what you have to do is project. So after you figure out what the bounds are for the y, what's your y min and y max, which may depend on x and y, then you have to project in the y direction, meaning what you do is you're going to create a shadow of the region E that the three-dimensional region E that you're integrating on the xz plane. So what does this really mean? What's this shadow about, or what's this losing depth perception thing about? To say this a different way, position yourself. So you've got to imagine taking yourself and moving yourself to have the y-axis look straight at you, look at you. That's like maybe the y-axis is pointing right at you, and then lose depth perception. So if you are located in the place where X, Y, Z. If you locate yourself right over here where the y-axis is pointing at you, and then you look back this way, whatever object you have, how does it land onto the XZ plane? That's what you're looking for. We're going to look at an analogy of what this looks like in two-dimensional space first because it's easier to draw. We're going to talk about an analogy over there first in the next part, and then we will do full-on examples of this.